Hey everyone, in this video let's take a look at question 286, walls and gates on Leetcode. This is part of our blind 75 list of questions, so let's begin. This is actually a premium problem on Leetcode, and that's why we're doing it on the Leetcode website and why the number here is different, but otherwise the question, the test cases, and the solution will be the same. So let's take a look. In this question, you're given an m by n 2D grid initialized with the following three possible values: -1, which means a wall or an obstacle; 0, which is a gate; infinity. Infinity means an empty room, and they use the value 2 to the 31st power minus 1 to represent infinity, as you may assume that the distance to a gate is less than infinity. We want to fill each room with the distance to its nearest gate. If it is impossible to reach a gate, that room should remain filled at infinity. Okay, so let's take a look at what this question exactly is saying. So go ahead and copy this. And again, for these premium type problems, we like to use Leetcode because they allow us to do it for free. Let's take a look. Okay, so in the input, we're given all of these values over here. And what we essentially want to do is that we want to transform all of these infinities essentially to a value, possibly remains at infinity, or it should be greater than 0, but it simply has to be the distance to the nearest gate, and the gate is represented by a 0. For example, in the case for this one over here, where is the nearest gate? Well, it would be, you would go down and then here, so that's why it's a value of 3. The negative ones don't change, so we leave them as they are. What about for this one over here, for this infinity? Well, the nearest one is actually right and then up, right? We also have another one left, down, and down, but notice how this is 3 spots away. This is 2 spots away. Similarly, for this one, it's just 1 spot away. And so in this question, essentially what we're asked is that we want to find the nearest element so that we don't actually go into this like obstacle over here. So we can go through all 4 directions and then figure out where we want to go. And there's also like another example over here. So we can take a look at this one. So in this one, we just actually have, looks like two values, right? So we have like a 0, a -1, or maybe I'll draw it like this: 0 and then -1, and we have infinity and infinity. And so really for this one, the shortest distance is actually just going to remain. What would it remain at? Well, it would remain at 1. It will go to 1 because there's a distance above here. And then for this one, we would go left and then we would go up. And that's how we would arrive at a 1, at a 2. Okay, so you understand what the question is saying. Now, how might we go about doing this problem? Well, in this question, like there's numerous approaches we can take, right? We could maybe do a DFS, we could maybe do a BFS. What's kind of like the appropriate thing to do? And why might we even want to do a BFS or a DFS? Well, first of all, it's a graph type problem, right? And anytime you kind of have like a 2D graph and a 2D matrix and you want to traverse it, maybe find the longest path in a matrix, or like shortest path or something like that, you want to kind of think of DFS or BFS. Okay, so we know we want to do that. And the question is here, like, what exactly might we want to do and which one would be better? Now, but both of them would work, right? A DFS would work maybe in the sense that where would we start off? I guess that's like the first question, right? Where would we start off? Would we start off at the 0 or would we start off at the infinity? And this question is actually very similar to a question we did before. And that question, the question was called 0, 1 matrix on Leetcode, which is pretty much identical to this question that we have here, in that for all of the zeros we wanted to find, or maybe it was the other way, for all of the zeros we wanted to find like the distance to the closest one, and we would replace that in the matrix and we would return that. So this question is kind of exactly similar to that one. And in that approach, we actually used a BFS, and we're going to use a BFS here as well. Well, why do we want to use a BFS? Well, the thing about a BFS is that you can do something called like expanding breadth first, right? So what does that mean? Well, what it means is that, for example, let's say we have all of these values inside of our BFS, right? And I'll go ahead and remove this, and I'll actually just put this over here. Okay, so the first question is, if we want to do a BFS, where can we do it from? Should we do it from either the infinities or should we do it from the 0? Because we can't do it from the -1s, right? Because these are like, they're like obstacles, so it wouldn't make sense to do it. So we have two choices, right? We either do it from the 0 or we do it from the infinity. What do we want to do? Well, in this case, I would actually say that it makes more sense to do it from the zeros. Why the zeros? Well, because if you think about it, from the 0, if we start off and maybe we add in both of these to our BFS calls, we can expand breadth first. We can expand level by level. What does that mean? Well, in the first BFS call, what we'll do is we'll try to expand. So these two will be in the queue, and we'll try to expand to this entire area over here, right? This entire area over here. Really, in this case, we'll actually just go ahead and we'll add in this infinity and this infinity because this -1 is here and we don't have anything on top. And then similarly, when we're processing this one, we'll actually just go ahead and add this infinity. But what does this mean that we're expanding breadth first and we're expanding level by level? Well, what it means is that in the first iteration of my queue in my breadth first search, I will just go ahead and handle these two items in the queue, right? And if you think about it, the items that these two can reach, right? The locations in the matrix that these two can reach, they have to be the closest ones. They have to. Because if you think about it, let's say like we had like a bunch of, let's say we had like a bunch of values here, maybe x, 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 maybe x, x. I'll just try to draw my grid just like here. And let's say we had these two values inside of my BFS. Maybe we had a value here, maybe we had a value here. And I want to know what is the closest distance of like this value here? Like how can we reach this value in the closest distance? Well, we can do it through our breadth first search, right? Because if you think about it, we're expanding breadth first. We're kind of expanding in like a circle around the point here, and we're expanding in a circle around the point here, right? So if you think about it, if we're expanding level by level, which means in the first iteration, we just go ahead and we expand on these two, then if I can reach this circle, this ending point, then I know that this has to be the shortest distance because it is right beside me, or it is like the closest one beside me. If I was to do it from here, I would go here, and then from here, I would have to go here. So notice how if I do something like that, it's actually 2 iterations, right? It's 2 iterations of breadth first search. In the first iteration, what do? Well, we can visit this one, and from here, we can only visit like kind of this one, right? And then the next iteration, well, from this bottom one here, we can go ahead and visit this top one, but we notice it's already been visited by this first iteration over here. And so when you expand breadth first and you do it level by level, which basically means that you only process the elements inside of the queue at a specific level. So for example, when we do this breadth first search the first time, we will just process this 0 here and this 0 here. The next time we do it, we'll process this infinity, and then this infinity, etc. So we'll only process level by level. We'll only process the amount of items that are on the queue at any given time. And so that's why we can guarantee that our distance will be the shortest distance. And we've done this in a couple of other problems. For example, word ladder, I think it was one of them was word ladder 0-1 matrix. And so if you want like more insight into this, definitely check out those videos. But without further ado, we can write the code in this one. And really, if you think about it, all we need to do is we add in all of the zeros, and then we keep track of like the levels, right? And when we arrive at an infinity, then we just replace the infinity with that specific level that we have. For example, if we start off from over here, then we expand, well, this is like level 1. And so this will be replaced by the value 1, which is exactly what we have here. Okay, let's take a look at how we can write the code for this. Okay, so what do we have? Go ahead and remove this. And I would just call this grid. I like to name these grid. And now what do we need? Well, we need to keep track of the rows and the columns. So length of grid and length of grid at 0. Now what else do I need? Well, I need my queue. And in a BFS, I also need like a visited set, which I'll call scene. And now what? Well, we argued that we want to add in 0 to the queue. Why do we want to add in 0? Because if we start from 0 and we expand breadth first, then when we arrive at infinity, we can then just replace the infinity with like the level or like the iterations of breadth first search that we have processed. So what might that look like? Well, first of all, what we need to do is we need to go through the list or the matrix for row in range and then for call in range. And then if grid at row and call, if this is a value of 0, then I will add this to my queue. And I'll also add it to my, well, actually, I don't want to add in the value itself. I want to add in like the row and the call, right? The row and the call. So I know like where I am. And then I'll also add it to my scene. So now what can we do? Well, now what we can do is we can start our BFS. So we started with while queue, okay, while queue. And now this is how we expand level by level. What we do is we keep a size, which is the length of the queue. And then we only process the amount of elements as per the size. So initially, in this first iteration here, we'll have 1, 2 elements. And then the next time we process it, we'll add in this infinity, we'll add in this infinity, we'll add in this infinity. Next time we'll have 3 elements, right? So in that sense, we're expanding level by level. So really in the start, my level is 0. And then every time I finish this for loop, I can increase by level by 1. Okay, so now what can I do? Well, let's say I'm in my loop now. So what do I need to do? Well, I need to pop from my queue, right? So I will do, I guess, roll call is equal to queue.pop, and I'll pop from the front because that's what we do in queue. And now what? Okay, so I can check actually if this value is an infinity. If it is an infinity, then I can just go ahead and replace it by the level. So I can do if grid at roll call, if this is equal to infinity, which I don't know how are they actually representing it as this 2 to the 31 minus 1? They might be representing it like that. Okay, so if this is the case, then I want to replace grid at row and call with simply the level itself, right? Now, what about the other case? What if this is not infinity, right? What if it's like a different value? For example, maybe it's like a -1. I guess we can handle the -1 after, but let's say that it's some sort of different value, right? For example, if we start off from the 0 here, and then I go to the infinity here, or maybe let's say we go to the infinity over here. So then we'll go ahead and we'll update this infinity to 1, right? But then from this infinity call, I also need to kind of go down here and then update this as well, right? So if you think about it, like we'll update infinity like many times, but we just because we have infinity doesn't mean we need to stop our breadth first search. We still need to breadth first search on potential lower like elements, right? Or like potential elements that are outside our boundaries. So actually like the only replacement I need to do is right here because we're only replacing the infinity. But now what I need to do is now I need to go ahead and see all the neighboring elements that I can add. So what can I do in this case? So basically check if we can add neighboring elements. So how can I do that? Well, we need to explore the 4 directions, right? Up, down, left, and right. So I can maybe have like a directions. And what I would do is I will set it equal to something like 0, 1, I guess 1, 0, and then -1, 0, and then 0, -1. And so what this allows me to do is I can do for dx, dy in dirs, and I can do new x is equal to row plus dx, new y is equal to call plus dy. So this will basically allow me to traverse all 4 directions. And now what? Well, now I need to make sure that first of all, I'm in the boundaries. And second of all, so let's maybe start with that. So let's maybe start with make sure I'm in the boundaries, right? So we can check, and there's a simple way to check this. We can basically check if new x, I guess we don't need the brackets, if new x is less than 0, or new x is greater or equal to rows, or new y is less than 0, or new y is greater or equal to calls. If this is the case, then we're actually out of bounds, right? So for example, it's like we're starting off in this first row here and we try to go up. So in that case, we're out of bounds. Now, what else can we do? Well, if this isn't the case, then what? Well, we have a couple of other cases to consider, right? First of all, this value that we're visiting, right? New x, new y, we want it to be an infinity, right? Like we don't want it to be another value. We don't want it to be a 0, right? We don't want it to be a 0 because we would have already actually processed all the 0. So we don't want it to be a 0. We actually also don't want it to be a 1, a -1 either. So we only really want to add this value if it is an infinity, right? If it is an infinity. So what I can do here, if it does not equal infinity, and maybe actually I can just 2 to the 3, 2 to the 31 minus 1. Maybe I'll just store my infinity like this. If it does not equal infinity, then I'll also continue because I only want to add it if it is infinity. Now what else? Well, what if this value here is actually in my like visited set, right? What this might look like, for example, is this value over here, this one over here that we're trying to find. In the first iteration, we'll actually add it to our queue based on like this location here, but we'll also add it based on our second iteration, like when we process this element over here. So really, I only want to add it to my visited set if I haven't visited it before. So what can I do here? Well, I can do if new x, new y, if it's in visited, that means I've already found a shortest distance to it. So again, I will continue. Now, if all of these cases are false, then I can go ahead and add it to my queue. So I will do queue.append new x, new y, but I'll also append it to my visited new x, new y. And that's basically all there is to this question. So let's take a look and we can just run it to see if we run into any problems. Visited is not defined, and I believe I called it seen. So let me just change all of this to scene. And I'll run it. And okay, so this one passes. Let's go ahead and submit it. And awesome, it passes. So don't really worry about this one. This is just false. But basically, this is how we can go about doing this question. So what we did is we took a BFS approach, similar to what we did in 0-1 matrix and word ladder. What we did is we started off at the zeros, and then we expanded breadth first, but we made sure that we only expand level by level. And so when we do something like this, it guarantees that the node you visit, it has the shortest path to whichever node like called it, right? And we can calculate that shortest path based off of this level variable over here. And so that's essentially what we did. If we arrived at infinity, we set that equal to the level, but we noticed that we can't just like continue. We have to actually add on more elements. Even if this current element was at infinity, we still have to add on more elements because it's possible that we haven't reached any of these elements so far, right? Just to kind of illustrate like what I mean in that point. For example, for this -1, we'll add in this infinity, but then we will never reach this infinity unless this one adds it to the queue, right? And so that's why we actually need to add it. And so once we do that, we do some error checks, and if it's all good, then we go ahead and append it to our scene and queue, and we arrive at the answer. So what about the time and space here? Well, if you think about it, the time, we're just going through the entire grid, so it's m by n, and like with rows and then calls, and then same thing for the space because we might potentially add in everything to our queue and our visited set, so the space is the same thing. Okay, thanks for watching.